with that in mind, let us talk about path homotopy. We say that a space is path connected if for 2 points, let's say this is a space, I have space, topological space X, I have 2 points like that belong to this capital X. If there's a smooth path like this from one to another, so if I can do for any 2 points on this space, then this type of spaces will be called path connected. Okay, any space that is made up of disjoint parts is path connected. So this is a comment. If I have any space that is made up of disjoint parts is path connected. Now, with all this in hand, let's first define what a homotopy is. We are finally going to introduce the formal definition of homotopy. So this is the formal definition on homotopy. Consider two different paths. Two different paths from x0 to x1. Again, keep this picture in mind. We'll discuss more later. For now, this picture will suffice that we introduced to get the idea of path connectedness. So we have two different paths from x0 to x1, let's say, and we are calling them, let's call them alpha and beta, and we have such that we have alpha 0 equals to beta 0 equals to x0, and alpha 1 equals to beta 1 is equals to x1. Okay, and again, just so that you can recall, we are using the interval that we introduced earlier from 0 to 1. This is a standard thing. Now, if this alpha and beta is such that alpha and beta takes your data from the interval, both of them, and maps those data to x, then they are said to be homotopic and written as alpha is equal. This is the equivalence symbol that we used, but that's the convention for denoting that these two paths are homotopic to each other. And another thing that you can say, oh, why this symbol? Well, in some sense, homotopic means whether they're equivalent to each other under some continuous deformation. So that's another reason of using it. So if this condition is satisfied, then they're said to be homotopic and written as this if there exists. Okay, let me use the there exists symbol. So this is the there exists symbol. If you don't know it, it means there exists. It's a shorthand notation. A continuous map F that takes numbers from a I cross I. That means you can think of this I Cartesian product I with a square, or so to say some, let's say xy plane. It takes two datas, so that's why I write it like this. And it also maps it to x such that your f of s comma 0. Oh, let me show you what this f actually looks like. It looks like this, s and t, and I'll explain what s and t is in a moment. For now, what you need to understand is that the leftmost one is the parameter s and the rightmost one is another parameter t. Okay, so when t is equals to 0, we are calling this alpha of s. When t is equals to 1, we are calling this beta of s for all s belongs to interval. Similarly, when this is 0 and t, we have x0, and this is 1 and t, this is just x1 for all t belongs to I. So now let me explain what this s is. This s will actually give you the curves themselves, and t is a parameter that will dictate, or so to say indicate, that what's happening in between alpha and beta. And I'll show you this with a picture again. So this map F is called a homotopy. If all these conditions are satisfied, then F, let's call it a connecting map, then the connecting map F is called a homotopy. Now, what all this mathematical jargon means, let's have a intuitive feel for it. The intuitive idea of homotopy. Let's say this is our topological space X. It's a big one, and this is a point, let's say this is a point x0 like this. This is a point x1, and I have two paths initially. One is this red one, that is, let's say alpha of s, where s belongs to my I interval that was given by what, 0 to 1. And I have another path over here, beta of s, right? So what does that map F does? Recall the conditions again. F of s comma 0 gives you alpha of s. So that means this alpha of s red line denotes to t equals to 0, right? And f of s1 gives you beta of s. This is where t equals to 1, right? And again, t also belongs to the same interval I that runs from 0 to 1. Now, when your s is 0, and let's say t is just some t, this is just x0. When your f is 1 and this is t, for any t belongs to I, this is just x1. And this actually agrees with all the definitions that you saw about paths earlier. So what does this t do actually? Well, what this t does is that, let's say this is t equals to 0, this is t equals to 1. Now, if you think of a movie, or if you think of this red line is getting deformed continuously into this orange line, then you can use this t as a parameter to identify that continuous deformation. That's what homotopy is. You are taking two paths and you are asking the question that are these two paths homotopic to each other. So essentially what you are asking is that can I take this red line and can I get a continuous deformation that will take me from this red line to this orange line. And in this case you can easily see that it's true, it's possible. Let's say this is equals to t is equals to 1/3. Let's say, what should I have here? Okay, let's say this is t is equals to 1/2. Okay, 1/2. Then I should have a 3/4 maybe. Yeah, I think so. So all the paths in middle are a family of paths, right? And all these paths between x0 and x1, in this case, all of these are equivalent to each other. Okay, so that's what a homotopy is, or a path homotopy is. That means whether two paths are equivalent to each other or not. And this relation that you saw, this alpha is equivalent to beta, two paths being equivalent to each other, you can actually show that this is also an equivalence relation as well. Now, instead of having such a nice surface, what if you introduce a hole like this? Let's say it's a green hole. Okay, can you deform? Okay, let me use another picture. I think that will help. So let's consider this topological space with a hole inside it. Let's say this is x0, x1. This is path 1, let's say alpha. Let's say this is another path. This is another path. This is another path. So let's say this is some beta, this is some gamma, this is some delta. Okay. Now if I ask you, is alpha and beta, are they homotopic? Well, that's true, because you can start from beta, let's say, and you can continuously deform it to go to the place where alpha is. It's like you're pushing this line like this, right? Similarly, if I ask you, is gamma and delta, are they homotopic to each other? From this picture it's pretty clear. Yeah, I can do that. I can start from gamma, let's say, and I can continuously deform it to go to delta. However, if I ask the question that whether beta and gamma, are they homotopic? The answer is no. Why? Because you have a hole in the middle. You cannot go out of this space, right? We have to do this continuous deformation by staying inside the space. So if you try to continuously deform it and go back to the place where beta is, at some point you'll have to cross this hole, and by doing that you are just leaving the space itself. So this is not a continuous deformation, so they are not homotopic. Similarly, gamma and alpha, delta and alpha, they are not homotopic to each other. However, this gamma and delta, they are homotopic to each other. This alpha and beta, they are homotopic to each other. So this is all I have to say about path homotopy for now. Now I want to make a comment again. So this is a comment. Just like path homotopy, we can also define homotopy for loops as well. So just like homotopy of paths, we can define homotopy for loops as well. But we will need a modification. And the modification we need is given below, given as f of 0 of t is equals to f of 1 of t is equals to x0. Because recall, what is a loop? You have a point like this, you go traverse some path and come back to the same point, right? And now let's say this is the loop alpha of s. So when your, let's say t is equals to 0, the parameter is 0. For any s and the parameter 0, this is alpha s. And when your parameter is 1, let's say this is beta of s. Let's say this is beta. Okay, so you can think of it as you are taking this alpha, and as t runs from 0 to 1, there is a movie going on that this alpha is getting continuously shrunk and shrunk and shrunk, and it's ending up on p, right? So this is the homotopy on the loops as well. And now we'll see an example, a very simple example. If we let x equals to Rn, where x0 and x1 are 2 points, and we, let's say, be clever and we define some f of s t such that f of st is given by 1 minus t alpha of s plus t times beta of s, and you can easily check that this is a homotopic map or a homotopy between alpha and beta. Okay, because if you look at these conditions that we talked about here in the case of the loop and in the case of this path, all these conditions, this map will satisfy all of them. So if you are ever given a map and you are ever asked to say, to make some comment about whether that's a homotopy or a homotopic map or not, you need to check that map against these conditions. If it's for path, you check this. If it's loop, then you check against these ones. Okay, now that we talked about some path and loop homotopy, we now want to define something called a homotopy class. So let's move on. Again, these are all the tools that we will be needing for the main attraction of this lecture, and that is called a fundamental group, which is also denoted as the first homotopy group, but we'll come back to that later. We need to develop some essential tools, so hold on with me and let's